This week we have a test, our second test of the semester in college algebra, and it covers functions and rates of change and properties of functions. So today I thought I'd work through the no calculator practice test. Unlike the last test where I just provided a review, this time I'll go ahead and put together a practice test for you to work through so that you can see sample style of each question. So here we go. Let's just jump right into it. Given the function number 1 is the point 2, 8 on the graph. Well, of course, you should recognize that the coordinate is supplying us with an x and a y value, and the thought is that when we substitute the number 2 into the function, we should see the number 8 as the function result. So I've just entered 2 into the formula here, the function here, and we're going to find out if that's equal to 8. And you are expected to do this without a calculator. So 2 squared is 4, 4 times 3 is 12, minus 2, minus 2. Well, 12 minus 2, that is 8. Does 8 equal 8? So I can say yes, 2, 8 is on the graph. For part B, if f of x is equal to -2, what is x? So we're saying that f of x is equal to -2, but f of x is also equal to 3x squared minus x minus 2. So a lot of you will just simply write this and solve. Since this is a non-linear function, we should make this equal to 0. I'm adding 2 to both sides, and I end up with 0 here. And this is really a problem that we had spent a fair amount of time working through during the last unit. This is a quadratic that could be solved by graphing or quadratic formula, etc., if we had calculator capabilities, but factoring, I think, is the way to go here since we don't have a calculator to work with. So if 0 is equal to x times 3x minus 1 after we factor, then we know that x is equal to 0, or 0 is equal to 3x minus 1. We set the two factors equal to 0, so I'll write this one this way just to be consistent. So here's one of our solutions, and after I add 1 and then divide by 3, then I see that my second solution is 1/3. Now for part C, list the x-intercepts, if any, of the graph. Well, x-intercepts occur when y is set equal to 0. So in other words, when does 0 equal 3x squared minus x minus 2? So this is the same style of problem we saw just a moment ago, only factoring this result is going to be a little bit different. So calculator is not available here, so we're going to have to factor this by hand and find our solutions manually here. Let's see here. I'm going to guess a 2 and a 1 in this position, and a negative and a plus. This pair of binomials will FOIL back together to make the original. So when we set 3x plus 2 equal to 0, and when we set x plus 1 equal to 0, we see our two solutions are -2/3 and -1. Those are okay answers, but since we're being asked to find the x-intercepts, I would label them this way: -2/3, 0, and -1, 0. X-intercepts are coordinates, not x values. Not x values solely, that is. So leaving them as x equal, I think, would be inappropriate. We would do the same thing for problem number 2. So I'm going to go ahead and pause the video here and let you work through these. I think the only difference here, or only question that may be interesting this time, is that the y-intercept, remember we find that by setting x equal to 0. So go ahead and pause the video and resume playback in a moment to check your work. And so here are the solutions that I would expect you to find. If x is equal to 2, what is g of x? Well, when x is substituted with 2, that simplifies to 4 over -3. It's perfectly fine to write this as -4/3 as well. That's perfectly fine. To determine whether this point is on the graph of g, we substitute 4 and hope to get a y result of 9/2. When I substituted 4 into this equation, I ended up with -6 as a result, which is not equal to 9/2. So no, 4, 9/2 is not on the graph. And then the y-intercept, we find that by setting x equal to 0. When x is set to 0, we get a y result of 2 over -5, or -2/5. And when reporting the y-intercept, just like the x-intercept, we should label this as a point. And I have the coordinate 0, -2/5. In question 3, we're answering some properties of the function. What is the domain of the function? So domain would be our x values, and it looks like this particular graph exists between -4 and +6. The range of the function would be our y values, and it appears that our largest y value is +3, and the smallest y value is -2. So our range exists between -2 and +3. So when reporting that, make sure you use interval notation. That's what we have been using mostly in this class. So for our domain, we would say that x must be an element of the set of numbers between -4 and +6. Notice I am including -4 and +6 here because there is a coordinate at that position. So we have to use our closed brackets here. For our range, we would say that the y results must be between -2 on the y-axis and +3 on the y-axis, and again inclusive, since we do have coordinates that do have a y value of -2, and we have a coordinate that does have a y value of 3. So those two endpoints are included, again using the closed brackets. Now for what values does f of x equal 0, we're asking for all x values that generate a y coordinate equal to 0. So you can imagine that there's a horizontal line here at y equals 0, or in other words, the x-axis. And we would say that x could be any of the three values. It looks like 0, 4, and 6. Now I've listed these three in a set of numbers. If you tell me that x equals 0, x equals 4, and x equals 6 separately, that's okay too. But this set notation is appropriate for this solution. We have a set of numbers that satisfy this particular function, or I'm sorry, this particular question. Now for part D, for what values is the function less than or equal to 0? Well, now we're talking about an interval of numbers, because we have this whole section here in purple that has a function result that's less than or equal to 0. So I'm going to have to switch from set notation again back to interval notation, and I would say that all x values between 0 and 4 produce a function that's less than or equal to 0. And since the function when evaluated at an x value of 0 does produce 0, and this function when evaluated at 4 also produces a 0, then I do want to include those endpoints, and we are going to use square brackets here. With number 4, we have to determine algebraically whether the function g of x is even, odd, or neither. Now there are a lot of even numbers and a lot of even exponents, so we might suspect that this is even, but remember we have to use algebra to make that happen. And the first thing we always do is we substitute in the opposite of x. The hope here is that when we simplify this expression after substituting the opposite of x, that we end up seeing the exact same thing that we started with. And I do believe that's the case. Negative x raised to the 4th power is the same as a positive x raised to the 4th power. Negative x squared is a positive x squared, so we have 8x squared plus 8. Since this expression is the same as the original, we can now claim that g evaluated at negative x is equal to the original. So therefore, this is the definition of an even function. So we know that, yes, this function is even. Now you should recall that if this expression did not come out to be even like it did here, our next step would be to factor out a -1 if needed. So we would factor -1 if needed. And if we can factor out -1 and spot our original function after doing so, then we'd have an odd function. Otherwise, the function would have been neither even nor odd. And that was our process for evaluating functions symmetry using algebra. Now, if we have a graph available to us, or if we had a calculator available to us, we might try graphing the functions to determine whether the function's even or odd. In this case, we have to remember our symmetry, and this appears to have reflectional symmetry about the y-axis. So every coordinate that exists over here has a mirror copy on the other side, and vice versa. So because of that mirror symmetry, I think we would call this function even as well. Remember, if it had rotational symmetry, if there was a 180-degree rotation about the origin, we would then call this an odd function. But in this case, we would say that it's even, and a simple explanation here is sufficient. We can say that it has reflectional symmetry. See if I can write that a little bit more clearly here. I don't know if reflectional is even a word, but it has reflexive symmetry about the y-axis, and I think that would be sufficient. Now, if you wanted to explain that for all x values, let's see here, f of x is equal to f evaluated at -x. If you wanted to make that claim, that would be perfectly fine too, because that's again a definition of even functions, but more of an algebraic approach for that description, whereas this problem was asking us to do so graphically. Now, using the same graph, determine the intervals on which the function is increasing. So increasing, it looks like from this position to this position, the graph is increasing. And then again here onward, there is an arrow, so we're going to assume that this is turning upward forever. This kind of looks like a trigonometric graph, but since we haven't studied those yet in college algebra, let's assume that this graph is pointing up and out forever from here. And then as far as decreasing functions go, then that means it's decreasing from -infinity to this position, and then from this stretch, or on this stretch of the graph. So we're increasing out here. There we go. So as far as increasing goes, I think we could say that it's increasing on all x values that exist between -pi and 0, and then again from +pi to infinity. And keep in mind here that we can't say that the function is increasing at this specific location or this one either. That's kind of the point where the function is changing from increasing to decreasing. So it's not really increasing at 0, and it's not increasing at an x value of -pi either. So we would leave the rounded parentheses in our interval notation here. As far as decreasing goes, I would say any x value from -infinity up to -pi. That would describe this first green section. And then again from 0 to +pi. That's showing the location where this graph is decreasing. Now for question 7, we need to identify the following if they exist. Sometimes these do not exist. Are there any local maxima or minima? Are there any absolute or global maxima or minima? Now remember, a local maxima is described as a point that contains the largest y value within a neighborhood of points. And then we often described maxima at a point of transition from an increasing graph to a decreasing graph. So as far as that goes, we do have a local maximum right here at 2, 3. So that's clearly a local maximum. As far as a local minimum goes, well, here's a local minimum if we look within that neighborhood. and here we have a local minimum as well. So we have two local minima. Those occur at 0, 0, and we also have one at 3, 2. Now, because this 0, 0 ends up being the lowest point of the graph altogether, we can see that this graph is increasing towards infinity at this asymptote, and the graph kind of terminates right here. Because of that, we might end up saying that this is not a local minimum after all, and instead we would say that that's an absolute minimum. So in that case, I would recommend that you eliminate that as an item in our local minima list, and we'll just stick with 3, 2. And then as far as our absolute maximum, well, it doesn't look like there's a single highest point in this graph because of this asymptotic behavior. This function is going to continue to increase upward indefinitely, so there is no highest point, and I think in this case we would say that there are no maximum points. Now these would be fine answers based on the descriptions we've been using in class. Some of you are familiar with that neighborhood description that we were talking about for for local maximum. And some of you would argue that, well, within this particular neighborhood of x values on the domain of this function, the y value is at a high point as well. So if you choose to write -1, 1 as a local maximum, I would be okay with that too. But I think removing this item from our local minima would be appropriate, so we only have one local minimum because the other minimum point is the absolute minimum. Now, lastly, we have a linear function, and we're going to answer this question. This one's real similar to what we saw in Math Excel, and the problems are essentially written with set notation or inequality notation, and we've been using interval notation for virtually everything, so I think I would like to see interval notation as the results here. But the question doesn't specify to use interval notation, so if you end up using set notation, I won't penalize you for that. It just is definitely the least common notation we've been using so far. So for part A, when does the function equal 20? Well, that occurs at this location here when x is equal to 5. And when is the function greater than 20? Well, the function's greater than 20 on this stretch of the function, so that occurs at this position to the left. So I would say something like this, that x has to exist between -infinity and 5, not including 5, because we wanted a function value to be greater than 20, not equal to 20. The x value of 5 produces a y result or a function result of precisely 20, and that was not included in this range. For part C, when does the function when is the function less than or equal to 60? Well, the function is less than or equal to 60 starting here at this point, -15 on the x-axis, and continuing in this direction. So the x values that produce a y result of 60 or less start here at 15 and continue indefinitely to the right because this is a linear function. So we would say x must exist from -15 to infinity. -15, of course, is included in this solution. Infinity is not because it is a concept, not a number. And that's it. That's our no calculator portion of the test. Lots of information is covered in here about function behavior and notions that we've talked about in class. But I feel if you can demonstrate your understanding for these style of questions, then that's a pretty good indicator of your understanding for this portion of the unit. Be sure to ask questions over these problems if you have any, and we can talk about them more in class tomorrow. Thanks for watching.